Maybe I go over there.
Hi, this is Dr. Culhane for Porpoise Robotics, and I'm now going to give a short explanation of what we're leaving behind here at Washington Math Science School and how it can be integrated. Then we can refer to this as we move forward. We are, of course, leaving behind the Sea Sparrow Manta Ray boat platform. The students here already built the Sea Perch, so that's something that the students here had made. We added to that a camera that is going to be waterproofed. It's a weatherproof camera. It's not yet waterproofed, but we're leaving that behind, and then you can waterproof that. The cable comes out here, and it is not yet connected to anything. We have not worked out how we're going to connect the camera yet. So that's something in progress, but the camera's there for you. The box here, this Otter box, is an Otter box, a waterproof box that has in it the MIT Sea Perch Sensor Suite PCB board. Now that board is not yet populated. It's not yet been completed with its components and its sensors. It will mount, when it's done as a shield, it will mount onto the Arduino. It's made to mount on the Arduino. And then it will have a light sensor for turbidity measurement. It'll have a depth sensor. It'll have a clock for time stamping, an SD card for storing data. It will also have a temperature sensor and a salinity sensor and a depth sensor. So that'll collect data on the mission and store it on an SD card. And when the Sea Perch surfaces, one can remove the SD card and load that data to Google's DigitalOcean. So that's the Sea Perch Sensor Suite from MIT, and they are publishing that curriculum for everybody. So that's what's going to go inside this OtterBox on the Sea Perch. So it has not yet been completed. Okay, this Arduino that goes with the Sea Perch Sensor Suite is sitting in a box here with an Arduino clone that Naja Crawford, one of your students, put together, that she soldered herself. It is reliant on an FTDI cable, which is this one here. And the FTDI cable has to be put on a certain way. It says to put green, that green wire there, where the GRN is there, and the black is ground at the bottom. So don't put it on upside down with these shiny pins facing up. Put it with the black face pointing up, and it goes on. It will work fine as an Arduino. It does, however, require FTDI drivers, which you have to download and install in the right folder for this to talk to the computer, to the USB. So that is something that you'll have to download. That's going in this box with a few extra pins. And so there you have the Sea Perch Sensor Suite Arduino, your own board that you built for any other kind of experimenting that you want to do. And you have, in this box, you have an XP breakout board, which requires, and I've written here, XP, requires a USB to USB mini. And this is the part that connects to the computer, so the computer can send signals wirelessly to the boat. The receiver is this XP shield, which goes on the Arduino. The XP shield mounts on that Arduino, and once again, we can pull out the one Naja did, and we can show you. Hello, how are you? And so we can put this and mount the XP shield onto the Arduino. And be careful how you do it. So now the XP shield is on the Arduino. In fact, what I can do is put those both in the same box, and we'll leave that there. Keep this on its own, and then the transceiver part, if I can carefully pull this together, we can probably put this in the same box. So there's your transceiver. This will receive the signals so that the Arduino can do its work on the boat, and you don't have to have a wire to it. So that's going in this box now, XP transceiver with an Arduino, and then we have an Arduino board here. Okay? Now that is being left behind. We also have these robotic toys that demonstrate sensing technology, and we were showing that this one, when you put your hand in front, it turns around, and it will be the same code that is driving the boat. What this uses is it uses an ultrasonic ping and potentially an infrared sensor. We've got both of those on this boat. We have the ultrasonic ping sensor here at the bow, and we have the passive infrared motion detector here at the bow, just like the one that you put near your garage door or your house to see if intruders are there. We've also put a color sensor here so that we can program it to look for specific colors, like for search and rescue, looking for orange or yellow or red. We can program that in. So those are the three sensors we're leaving you with. Another sensor that you can put on, but that we have not left you with, is a touch sensor, as demonstrated by this little Radio Shack robot. The touch sensor in this case changes the wheels when it gets touched in the front and the back. And so, as you can see, he just goes forward and back as he's touched. You would be able to mount those whiskers on the boat in various locations, so when you're pulling into port, you can do it. We don't have those for you yet, though. But that is the concept that we have. So what do these sensors talk to? These sensors are talking to this Arduino board here, an Arduino Uno. They're being talked to through an Adafruit motor shield, but the pins here, the female headers, belong to the Arduino underneath. They have nothing to do with driving the motors. They just come up from it. That's a part of the shields. They all have female headers, so you can still talk to the Arduino underneath. So the sensor signal is going into this Arduino pin, and then the positive wire and the ground are going into positive, 5 volt, and ground. And we do that with these as well. We'd assign them different pins. That is letting these sensors talk to the Arduino. The Arduino is talking to the motor shield. This Adafruit motor shield has 2 H bridges. Those are the integrated circuit chips that control the motors, one on either side, and each H bridge can handle 2 motors. 2 motors here, 2 motors here, M1, M2, M3, M1, M2, M3, and M4. But each of these chips can only handle 1.2 amps peak. 0.6 amps continuous. Because I've put 2 motors in here, because the Sea Perch has 3, 1, 2, 3, I doubled the chips to hope to double the current. It's not an easy practice, and I don't recommend it. So what we've done is we've put left motor into motor 1, motor 1 here, right motor into motor 3 on the other side, and the up and down motor into motor 2. That's because we could have the left and the right motors on at the same time, driving the boat forward, and be having them each driven by a single chip. And those motors draw 0.5 amps continuous, and their peak is about 1, so they're within the limits. But when we want to use the third motor, going up and down, which is motor 2, we generally shut off the front motor and back motor. So you're driving forward, you shut off the motors, and then you turn on the up-down motor. Just in case they're on at the same time, however, we've got that double bridge. You see, that was the point of that. But you shouldn't, the code should always shut off those motors. If you want to run them at the same time, then we need more powerful chips in here. And this is being connected by USB to the computer. And I have a switch, the toggle switch. The power for the motor shield is coming from this 11.1 lithium polymer hobby battery, and that's going through this switch, and then it's turning on the motor shield. That is coming in here, ground and positive on the motor shield, coming from the switch. The power to the sensors is coming from the Arduino itself, which is powered by the computer. When you release it from the computer after downloading your code, you can put a 9-volt power source in any Arduino board through here. So a 9-volt battery that you put on the boat. And it shouldn't be just a typical 9-volt. It should be a heavy-duty 9-volt for hobbyists, because they go down pretty quickly when it's a regular 9-volt.
Is there a connector?
You have to make it. Got to make your own connector for it. So that's what you would do when you tether out. Similarly, when we're controlling the boat motors, these boat motors are more powerful. Their continuous draw is about 0.8 amps, and they're instantaneous. When you start them up, the inductive draw can be as much as 1.5. So we use a different motor shield. This is a DF robot motor shield mounted on an Arduino. It only handles 2 motors, and each one can handle 2 amps. So it's twice as much about as this one. So you can put up to 2 amps here and 2 amps here, and these, if they get slowed down, they can easily get up to 2. However, if they get snagged completely, they can draw up to 5 amps we've measured. If that happens, Mr. Nuristani put fuses in that'll blow at 2 amps. and then you've protected your board if it got caught in seaweed, for example. And then that power is coming off of this 11.1 lithium battery and powering this motor shield here, so it can talk to those two motors. Because it's mounted on the Arduino can also use its pins that come up here for driving, for example, these servos. So we've taken the signal pins, which are in the code 9 and 10, it can be anything, and we're going into the signal pins of the servos and using the positive and negative off the Arduino, the 5 volts, through a breadboard so that we can then power the servos from the Arduino. And this one, again, when you disconnect it after you've loaded your program, would be powered by a 9-volt battery here. Okay? Then you're able to power the servos. This can handle up to 8 servos. So you can put a servo at this joint and a servo at this joint for the claws. We don't have that yet. We started putting one on, but we don't have the right parts. So you'll probably have 3 servos for this robotic claw, 3 for this. That's 6 servos. That should be able to handle that. If not, we switch to this board and use this Arduino through this motor shield to handle the servos. Read about how many servos you can handle per board. But we have plenty of servo capacity on this. We're providing, this is a telephone jack, 8-pin for the Arduino, for the Sea Perch. It used to go into a Sea Perch controller. We rewired this. It now goes into this, and then that talks to the motor shield. Okay, and that is it for what we are leaving behind here, although we're also leaving behind this boat as a test platform for landing craft on it and working on that, flying air missions. This Sea Perch that you built has the new motor concept of putting a T so that the motors can easily be taken out and moved and put back in or replaced without being difficult. In the original case, you would have to snip these wires, and that's a hassle, and you couldn't do anything. We've put the same functionality on the boat. The boat motors can be taken out. Motors that don't draw as much current could be put in. So you have that flexibility, and you can rotate them. The other thing you could do is take these out and put in motors with wheels on them, and you can test this in your classroom without any water, testing all the code simply by snapping wheels in and putting a front caster on or something, and then driving the boat that way. So we're trying to make it so that everything is fairly easy to do. As you see, the materials are all simple. Here, for making another boat, the entire boat is made out of these sheets of plastic. This one is made so you can make the nose cone part. Just step 1, this would go like this, and these would fold down after you've cut this pattern out. Then would go the cross grain part, because this grain is going this way, this grain is going this way, and that gives you structural reinforcement like with plywood.
Yes.
And then on top of that would go the wing platforms cut out, and then that gives you surface to put solar panels, to put your batteries in your Arduino shields. So that's the whole thing. PVC, water bottles, any other type of flotation device you want for the boat. It's the same concept. This has an endoskeleton made of PVC. This has an endoskeleton made of PVC, a skin made of readily accessible plastic. So it all should work. It's in progress, and we look forward to what you come up with for improving the Porpoise platform.